We're going to finish up the second half of 7.5, which is the quadratic factors. Yesterday we looked at linear factors. So here's kind of like a summary for the guidelines for solving the basic equation. The first one's for linear factors. So there's two guidelines you need to know, and you guys can just finish this on the same notes paper from yesterday. The two guidelines you need to know to solve the basic equations that involve linear factors, like we did in yesterday's video and then in last night's homework or in today's homework, is that you substitute the roots of the distinct linear factors into the basic equation. And that was like what we wrote up at the top where we said that, I'll move that back down in just a minute. Up at the top we said substitute convenient values into the equations to obtain equations for a and b, or in other words, convenient values are values that make the factors equal to 0. And so kind of like what we did here in this example 3, we wanted to find out what would make this equal 0. So that was the root of this factor, which was 1. And we wanted to find out what would make this equal 0, and the root of that factor is -3. So that's all that these two guidelines are talking about, or that this first one is talking about. Substitute the roots of the distinct linear factors into the basic equation. That will help you to get rid of extra variables so that you can solve for just the one. The second guideline says for repeated linear factors, so if any of the factors repeats themselves, you need to use the coefficients from guideline 1 to rewrite the basic equation. So, for example, once you solve for a or b or c or whatever it is, you're going to, for the repeated linear factors, you're going to need to, you're going to need to substitute in whatever coefficients you've already found into the new equations with different values so that you can solve for the repeated linear factors. Today we're going to be looking at the guidelines for solving basic equations that involve quadratic factors, so you can write these 4 down as well. The first guideline is to expand the basic equation. So if there's no way to eliminate any of the factors to begin with, you can expand it. And what it means by expand is just to multiply everything out. The second one is to collect terms according to powers of x, which I'll show you today. But essentially, like group all the x cubed terms together, all the x squared terms, all the x terms, and all the constant terms. The next one is equate the coefficients of like powers in order to obtain a system. So you're going to leave the left-hand side of the equation alone, and you'll equate the coefficients of the x cubed power on the left side with the coefficient of the x cubed power on the right side, so on and so forth with all the other powers of x. And then last but not least, you can solve that system of equations. So go ahead and pause the video if you need more time to write this down. We're going to do 2 examples out of your textbook, so go ahead and copy this down, and then we'll look at those. All right, so the 2 examples we're going to look at are on page 512 and 513 in your book. It's example 3 and example 4 for quadratic factors. So this is the first one. So yesterday when we were looking at linear factors, we had to factor the bottom and find all the linear factors. And this one we still have to factor the bottom. So if I rewrite this again, I get that we have 2x cubed minus 4x minus 8 divided by, this factors to x times x minus 1 times x squared plus 4. So these first 2 factors are linear factors, and neither of them are repeated, so those are going to be just like yesterday. And then this one is actually a quadratic factor, so we're going to do this one a little bit differently today. There's no way to simplify that one anymore. We can't separate it into anything else, so that one has to stay quadratic. So for my linear factors, just like yesterday, we have a over x for the first one. We have b over x minus 1 for the second one. And then for this new one, remember you have to add in that x on the top, so we have cx plus d divided by x squared plus 4 for that quadratic factor. So that's the difference for quadratic factors, is you have to have a cx plus d on the top. Alright, so from here, I want to get my basic equation, so I'm going to multiply this whole thing by the least common denominator, which is x times x minus 1 times x squared plus 4. So on the left-hand side of my equation, that entire denominator cancels, so I'm left with 2x cubed minus 4x minus 8. On the right-hand side, for the first term, I have a over x, so the x's will cancel. I'm left with a times x minus 1 times x squared plus 4. For the second term, I have the b times the x minus 1 term will cancel, so I have x times x squared plus 4. And then for the last one, both the x squared plus 4 will cancel, so I'm left with cx plus d times x minus 1. So if I look at my guidelines for solving quadratic, the first guideline says to expand the basic equation. However, I would not do that until you've made sure that there's nothing you can eliminate yet. So first thing I would do is I would look for the roots of the distinct linear factors so that you can substitute them into the basic equation to cancel out some of them. So for example, if you substitute in a 1, all right, if you substitute in use x equals 1, if you use this, you're going to notice that this a term is going to cancel because it has that x minus 1 factor. And you're going to notice that this cx plus d term is going to cancel because it also has the x minus 1 factor. So that's going to help us solve for b. So let's do that one first. So if I do that, I plug it into the left-hand side. I get 2 times 1 cubed is just 2, minus 4 times 1 is negative 4, minus 8 equals, the a term cancels, I'm left with b. I plug in 1 to x, so I get 1 times 1 plus 4, which is 5. So over here on the left-hand side, I have 2 minus 4 minus 8, so that's 2 minus 12, which is negative 10, equals 5b, which means that b equals negative 2. So that helped me get my b term. Let's see if there's anything else I can substitute in that will cancel out some other things. What about if I use x equals 0? X equals 0, the a term won't be affected because that doesn't have that as a solution for any of the roots. The b term will cancel because it has an x, and the cx plus d term will cancel because it also has an x. So that's going to help us out. So let's try this one. If I plug it in the left side, I get 2 times 0 cubed, which is 0, minus 4 times 0, which is 0, minus 8, equals a times 0 minus 1, which is negative 1, times 0 squared plus 4, which is just 4. So that means I have negative 8 equals negative 4a, which means that a equals 2. So far I've been able to solve for my 2 linear factors, which hopefully should be the case most of the time where you're able to solve for those 2. The cx plus d, there's nothing we can plug into that one that would help us get rid of the a and the b terms because there's nothing you can plug into this x squared plus 4 in order to make it equal 0. So instead what we're going to have to do is we are going to have to, solve it using a system of equations. So we know what a is, we know what b is. I'm going to erase some of this work, so pause it if you haven't gotten this yet. So I'm going to keep track that a equals 2 and b equals negative 2. Put that right up here. A equals 2, b equals negative 2. So we can just use random numbers now and substitute them in, and then we'll just plug in the a and the b that we know, and we'll solve for a system of linear equations in c and d. So the first one I'm going to use is I'll use, let's see, we've used 0 and 1. I'll use negative 1. So I have 2 times negative 1 cubed, that's negative 2. Negative 4 times negative 1 is positive 4, minus 8, equals, a is 2, so I'm going to plug in 2. Then negative 1 minus 1 is negative 2. Negative 1 squared plus 4 is 1 plus 4, that's 5. Plus b is negative 2 times negative 1 for x, and then negative 1 squared plus 4, again that's 5. Then we have c times negative 1 plus d times negative 1 times negative 1 minus 1, which is negative 2. So over here on the left, I have negative 2 plus 4, that's 2. 2 minus 8, that's negative 6. This first term, 2 times 5 is 10. 10 times negative 2 is negative 20. The next one, negative 2 times negative 1 is positive 2 times 5 is 10. For the next one, I have negative c plus d times positive 2. So if I move my constants over to the left-hand side, I have negative 6, add 20 to that side, and then add 10 to that side. Makes, let's see, that's negative 10 plus 10, 4. And then on the left-hand side, if I distribute the 2, I get negative 2c plus 2d. All right, and that will be my first equation that I'm going to use. So I need one more equation besides this one so that I can use it as a system of equations. So the other number I'm going to try and plug in is going to be, how about x equals 2? So if I plug in 2, I get 2 times 2 cubed. Well, 2 cubed is 8, times 2 is 16, minus 2 times 4 is minus 8, equals, a is 2, x minus 1, so 2 minus 1 is 1, 2 squared plus 4, that would be 4 plus 4, that's 8, plus b, which is negative 2, times x, which is 2, times x squared plus 4, so 2 squared plus 4 is 8. Plus c times x, so if x is 2, that would be 2c, plus d, times 2 minus 1, which is 1. So 16 minus 8, that's 0. 2 times 1 times 8, that's 16. Negative 2 times 8, that's negative 4 times 8, which is negative 32. And then if I distribute the 2 into the 2c plus d, I get plus 4c plus 2d. So let's move the constants over to the other side. I have 16 minus 32, that's negative 16. So if I add that to the other side, I get 16 equals 4c plus 2d. So here are my two equations that I have now. And to solve for those last two, to solve for c and d, I need to solve that system of equations. So I have two equations and two variables. I can solve them using systems of equations in order to figure out what c and d are. So I'm going to do it by elimination. Let me just erase some of this work so I have room. All right, so my first one is 4 equals negative 2c plus 2d, and 16 equals 4c plus 2d. All right, so using elimination, I can eliminate the two d's by just multiplying the top equation by negative 1. So I have negative 4 equals positive 2c minus 2d. And then on the bottom one, I have 16 equals 4c plus 2d. My 2d's cancel, so I get 16 minus 4, which is 12, equals 6c. So c equals 2. And then if I just plug that back into one of my other equations, I get 4 equals negative 2 times 2 plus 2d. So that would be 4 equals negative 4. Add 4 to both sides, you get 8 equals 2d, which means that d equals 4. So now I know what a, b, c, and d are. So I can finally, took a while, but I can finally plug them back into my partial fractions. So c equals 2 and d equals 4. Let me erase this now. All right, so that whole process was solving the basic equation to figure out a, b, c, and d. So now I'm back to my integral again, the integral I want to evaluate, and I'm going to use this piece here and plug in a, b, c, and d so that I can integrate that. So a is 2 over x plus b, which is negative 2, so I guess that'll be minus 2 over x minus 1, plus c, which is 2x plus d, so plus 4 over x squared plus 4. All of that with a dx right behind it. So again, the point of doing these partial fractions is that we're able to integrate a lot easier. Now I can split up this integral, and I can also split up that last fraction by separating the numerators. So I have the integral of 2 over x dx minus the integral of 2 over x minus 1 dx plus the integral of 2x over x squared plus 4 dx plus the integral of 4 over x squared plus 4 dx. All right, so if we're looking at all of these integrals, most of them are basic integration rules. One of them is one of the more difficult ones, but still not too bad. So for this first one, the integral of 1 over x, if I just take that 2 out, the integral of 1 over x is ln of x, or ln of the absolute value of x. So this one would be 2 ln absolute value of x. minus, again, if I take that 2 out, I get 2 times ln absolute value of x minus 1, because that's the integral of that one. For this next one, the 2x over x squared plus 4, if you remember back to the beginning of this section, we learned that that can be the natural log as well. So that one is actually the natural log of x squared plus 4. I don't need to do absolute value with that one because x squared plus 4 will always be, what am I trying to say? Positive. And the reason we can do that one is because if you think about that as the chain rule, the derivative of the natural log of x squared plus 4, this piece here, is 1 over x squared plus 4 times the derivative of the inside, which is times 2x. And so that gave us what we had originally, which was right up here. So that's the integral of that function that we have up there. So that's how we figured that out. All right, and then the last one is not one of those simple ln ones. It's actually a little bit different. So when you have an x squared plus 4 with a constant on the top, you can actually look at your integration rules on 388 to figure out that it's 2 tangent inverse or arctangent of x over 2. But I'll let you look at those rules to make sure that you agree with that. All right, so that is how we're going to leave our answer. And that is the integral of that fraction that we had up at the top. Kind of long, took us a long process. These quadratic ones do definitely take a little bit longer. But that's how you do it. All right, this is the last example that we're going to do together. It's on page 513 in your book. This down here is a quadratic factor again, and it's actually a repeated factor, so we're going to have to use that repeated rule. It can't factor anymore. X squared plus 2 is the final factorization of that. So when we factor this, I'm going to get 8x cubed plus 13x divided by x squared plus 2 squared. So when I break that up into partial fractions, I get ax plus b divided by x squared plus 2. And then I have to account for the second linear factor as well. So cx plus d divided by x squared plus 2 squared. So the first thing first is I want to solve for my basic equation. So I'm going to multiply by the least common denominator, which is x squared plus 2 over 2. Squared. On the left-hand side, it gets rid of the entire denominator, so I'm just left with 8x cubed plus 13x. For the middle term, the ax plus b divided by x squared plus 2, one of the linear factors will cancel, so I'm left with ax plus b times x squared plus 2. And then for the last one, the entire denominator cancels, so I'm just left with cx plus d. Now, there's nothing I can plug into x that will make any of these a's or b's cancel out, so I'm going to go back to my guidelines that we wrote down at the beginning of the video. The first one says to expand the basic equation, so I'm going to expand this term as much as possible so that I can have everything as their own individual terms. So I'm going to leave this side alone. 8x cubed plus 13x equals, if I expand this side, I get ax cubed plus bx squared plus 2ax plus 2b plus cx plus d. Now from here, the next step says collect terms according to powers of x. So I want you to notice we have an x cubed over here, and we have 1x cubed over here. So that's all that there is for x cubed, so those ones are already collected. We have an x squared term here, but there's no x squared term on this side, so that actually means that the x squared term has a coefficient of 0, so we'll use that fact in just a minute. Here's a 13x, and I see a couple x terms over here, so we're going to group those together. And then there's no constant term on this side, but there is two constant, I'm sorry, that's not constant. There are two constant terms on this side, so we're going to group those together as well. So I'm just going to rearrange this so that it looks like 8x cubed plus 0x squared plus 13x plus 0, just so that it's in standard form, equals x cubed times a, and you'll see why I'm doing that in just a minute, plus x squared times b, plus x times, there were two of those, so 2a had an x in it, and then plus c, that one also had an x in it. And then the constant term was plus 2b plus d. That was my constant term at the end. So notice here now that I have all of these. I have x cubed and I have an x cubed on this side. I have an x squared, I have an x squared on this side. I have an x and I have an x on this side, and I have a constant term and I have a constant term on this side. So I'm actually going to set their coefficients equal to each other. So look what I do. For the x cubed terms, I'm going to set the coefficient of x cubed, which is 8, equal to the coefficient of the x cubed term on the other side, which is a. So now all of a sudden I know what a is. A is 8. For the x squared term, I'm going to set 0 equal to the coefficient of the x squared term on the other side, which is b. Oh, now I know what b is. B is 0. For the x term, I'm going to set the x's coefficient, which is 13, equal to the coefficient of the x term on the other side, which is 2a plus c. And we know what a is, so we're going to solve for c in just a minute. And then for the last one, I'm going to set the constant, which is 0, equal to the constant term on the other side, which is 2b plus d. And again, I know what b is, so I can solve for d pretty easily. So on this one, if I plug in a, I get 13 equals 2 times 8. That's an 8. Plus c. So I get 13 equals 16 plus c. So if you subtract 16 from both sides, you get negative 3 equals c. And then for this one, if I plug in b is 0, I get 0 equals 0 plus d, which means that d equals 0. So I know that a equals 8, b equals 0, c equals negative 3, and d equals 0. So that one was actually much easier to solve using those guidelines. And now I can plug those back into my partial fraction. So I have the integral of ax plus b, so that's 8x plus 0, divided by x squared plus 2, plus the integral of cx plus d, so that's negative 3x plus 0, divided by x squared plus 2 quantity squared. Let's include a dx on both of these. So now if we're looking to integrate both of these, the first one falls under the rule of, kind of like in that last example, where you have, let's see how to put this. You can say that it's the ln of x squared plus 2. It's going to have a coefficient in front of it, but think of the derivative of what I just wrote. The derivative of ln of x squared plus 2 is 1 over x squared plus 2 times 2x. So remember, it has an x term on the top. That's why I can do that. That's why it follows this rule. It should only have a 2 on the top, so the fact that it has an 8 tells me that it should be multiplied times 4, so that it makes it 8. So that's the integral of that first one. For the second one, I have a negative 3x on the top and an x squared plus 2 squared on the bottom. So for the second one, it actually follows the rule of the power rule, because again, it has that x on the top, but the fact that it's squared on the bottom, it tells me that it was originally, I'm just going to do some scratch work down here so you don't have to worry about writing this down, that it was originally 1 over x squared plus 2, because if we look at the derivative of that, all right, we're looking at the derivative now. The derivative of this, if you think about x squared plus 2 to the negative 1 power, would be negative 1 over x squared plus 2 squared times the derivative of the inside, which is 2x. So that actually kind of looks like what I have right here. I have that negative accounted for. I have the x on the top accounted for. The only thing I don't have accounted for is the extra 3 that's there, but then also I need to get rid of this 2 somehow. So here's how I'm going to write the integral. I'm going to write it as the extra 3 I'm going to account for just by multiplying it on the top. And the extra 2 I'm going to account for getting rid of by just dividing by that 2 down here. So I have x squared plus 2 plus a constant. So make sure that you guys are studying these rules. Make sure that you guys know these rules by heart, how to figure out the integrals and things like that, just to make sure that we are all on the same page. All right. So that's it for today. I'll assign you guys some homework so you guys can practice some of these.